Let's continue with the decorrelation part of the spatial efficient coding. This K0 matrix is this n by n matrix. Each row is an eigenvector. Each row, row 1, row 2, and so on, is an eigenvector of the signal correlation matrix Rs. To understand this intuitively, let's recall when n equal to 2, so this vector becomes two-dimensional vector, S1 and S2. Yeah, and in this case, this matrix n by n matrix becomes 2 by 2 matrix. Yeah, 1 over square root of n become 1 over square root of 2. We recall that we use this in our stereo coding example. And when you get this S plus is the average and summation of the two signals, and S minus is the difference of the two signals indeed. Yeah, and normalized by 1 over square root of 2. And therefore, analogously, the first component, just like the summation signal, it is the summation or average of all these n spatial pixels. So therefore, this is the average of the whole image. And you can call this the DC component of the image. While all of this, second all the way to nth component, they are just various types of differences between these n pixels. And these differences are described by what kind of spatial waves are there. So let's look in detail. First, you see the first wave is K1. Okay, K1, X1, K1, X2, K1, Xn. So this is a wave in space with frequency K1. And this frequency K1, for instance, this is I equal to 1, yeah? And this Xn is just the spatial extent of the whole image. So I equal to 1, K1 equal to 0. So therefore, the exponential to 0, this is 1, 1. So all of these elements are 1, 1, 1, 1, 1. So you have all these ones acting onto this spatial pixels. You get your first component, which is the average of image pixels normalized by this constant. Yeah, and so now for the second row, you have this K2 is no longer equal to 0. It's a small number, such that across spatial extent from X1 to X2, and so it just have the whole wavelength, it just extending to the whole image once. Okay, and now this acting onto the whole image is taking the whole image weighted by a spatial wave, which is just a whole wavelength extending the whole image. So this gives the first, the Fourier component for the first wave that's having non-zero frequency. Yeah, and the second component and the third component and so on. The frequency gets higher and higher and higher as this K value becomes bigger and bigger and bigger, until the last row you have this frequency is really high frequency. You achieve the sampling limit of the image, which we call the Nyquist sampling limit, yeah, of the image. And so that's why how these differences are calculated in these kind of waves. We can even calculate it out. For example, let's calculate for SKA. Imagine this KA is, let's say, A equal to 2, so it's this component SK2, yeah? And so therefore, you plug in, okay, all these values times that value, you plug it in. The sum over all these x, you can also write it in this integration form. So summation over x becomes integration over x. S subscript x becomes S as a function of x. This is a function of x, which is a spatial image. This is a Fourier transform of this image for the frequency Ka. This is written in a discrete form. So therefore, this number really is the Fourier component of the original image for the frequency Ka. Yeah. And so therefore, given each image, you get all these Fourier components. And of course, you can have different images and you have average over the image. You can say, what is the average signal power for this component? Then you take this component magnitude squared and average over the ensemble. Remember, this bracket means the average over ensemble of all the natural scene images. And you remember, once we calculate out for this 2 by 2 matrix, really it becomes the eigenvalue of the signal correlation matrix. And this is the intuition that you can just get what this decorrelation transform is. Here is an example of the Fourier components using this example image. Because the image is two-dimensional, the Fourier frequency is a two-dimensional vector, yeah, with component kx and ky. Okay, because the Fourier wave can propagate vertically or horizontally or in any direction, so that the k vector can be in any direction, and kx spans from negative to positive, and so is the ky with 0 in the middle. It is measured as cycles per image, meaning that the Fourier wave has the wavelength such that for the whole image, it can have that many cycles of wavelengths for the whole image. And so, of course, the higher the frequency, it gives more cycles for the whole image. You can see that the magnitude of the Fourier component, when you take the magnitude, yeah, it is highest when the frequency is 0, yeah, and this is the DC wave, because natural images have pixels correlated. When you average over all these, sum over all these pixels, it should have the highest value. That's why the first component for the 0 frequency is the biggest, yeah, and we can also view it in this plot, which plots this magnitude squared over versus the magnitude of this frequency k cycles per image. Okay, and for each blue dot is actually example magnitude and example direction. And so because you can go over all these directions, if you average over all directions given the magnitude, you get this green curve. If you then average over all images in natural scene, you should get this red curve. It goes as 1 over k squared. And so it really decays very quickly with the frequency. And this 1 over k squared is the trend that signifies the scale invariant property of the natural scenes. And so in a gist, you can see this spectrum is such that it has the highest magnitude at the DC frequency and decays very quickly as the frequency goes up. This value is, the magnitude squared is, as a function of frequency k, is called the power spectrum of an image. Yeah. So far I just gave you the intuitive description of what this decorrelation transform gives and what is the Fourier components of an image and what is the power spectrum. If you want a more rigorous understanding, more mathematical understanding, you can see the textbook or you can follow the rest of the video. This K0 is in fact this n by n matrix. And then we know that each of these, in fact, this row vector must be an eigenvector of this correlation matrix for this decorrelation to work, yeah? So in particular, this K0 is made of lots of row vectors. So each of these row vectors is one of these, yeah? So this first row vector is this one, second row vector is this one, and so on. And in particular, more formally, you write this, the K1, this is actually a dagger. Really, it's a row vector. This is the corresponding column vector, but it's complex conjugated from each of these rows. Okay, this row now becomes this column. Each of these negative sign becomes the positive sign. So this is the column vector, yeah, and this column vector is an eigenvector of this R matrix when this matrix satisfies this form, yeah, and this is called a topless matrix in which all these, diagonal lines, whether it's exact diagonal or off diagonal, they have the same values, and this is a topless matrix. And for topless matrices, their eigenvector are these Fourier wave-like vectors. You can show that this is indeed the case. So in fact, if we make this correlation matrix act onto this eigenvector, okay, so like that, this row act on this column, okay, it's a summation over all the elements of this column, summation over J, yeah, okay, and then just write this term out, and each of these elements is copied down like that, and then you write it out like this form. In fact, each of this term is now written this way. The reason is each of these elements, yeah, xi, xj, depends only on the distance between the two pixels, xi and xj. This correlation depends only on the distance, yeah, that's translation invariance. And this term is written out into a multiplication of these two terms, yeah. So exponential ik xj is still ikxj here, but you add an ikxi here, and this is a negative and this is a positive, yeah, ikxi here, they cancel each other. So this single element is split into two, so you can say still summing over j, same, so this is equal to that, okay. And now we can see that this is exact the ith element in this vector, yeah, because now this is xi, so it's the ith element, and this is a constant, okay, because as a topless matrix, as you sum over this over J, it does not depend on what xis because of the topless matrix, the property of the topless matrix, yeah. So this constant is in fact the eigenvalue of this matrix for this eigenvector, yeah, this eigenvector. So we prove that this is indeed an eigenvector. This Fourier wave is an eigenvector of this correlation matrix. In addition, each of these k's, yeah, in each row really is the frequency of the Fourier waves, the spatial frequency. So k1 is the first frequency, k2 is the second frequency, and so on. And all these frequencies, ki for the ith wave, satisfy this requirement. This is the total extent of the spatial extent, okay? And so therefore, when the first wave I equal to 1, this frequency equal to 0. So first wave is the zeroth frequency. This is kind of a DC Fourier wave. And when I equal to 2, this whole wave will expand just one wavelength over the whole spatial extent, and two wavelengths and so on. So therefore, these different frequencies, if you integrate over the whole spatial extent, they are all, each of these vectors are orthogonal to each other as what eigenvectors should be, yeah. Now let's also try to calculate what each of these Fourier component looks like, yeah. So just multiply a row with this column. So for instance, this is, eighth component, first, second, third, and so on. So this is the eighth component. Let's say it's a second, okay? So you multiply the second row with this column. This is how you multiply out, summing over these x, okay? Each row has the same k but different x, and so the sum over x. And you can also write it in this integration form. So sum over x become integration over x, and s subscript x is now written as x, okay, just a spatial function of x. So you see this is a Fourier transform of a spatial function x, whether it's in a summation form or integration form. So this really is the Fourier amplitude of the original signal s, yeah. And we can also try to calculate what is the average power of this Fourier wave, yeah. And so therefore you take the Fourier amplitude, take its magnitude squared, and do the ensemble average. Okay, so let's write it out. Now, one sk, we just write it like sk like that and copy it down. The other sk is actually complex conjugate. That's why now we write it as x prime, just to separate another sk. And complex conjugate, it means this minus sign becomes plus sign, okay? And so these two things multiply with each other. It's squared, yeah? And the ensemble average. Now we're going to take this ensemble average over the whole thing as the ensemble average over this signal, yeah? Okay, so this is how we do it. Ensemble average just over these relevant signals. These are just integration mathematics, yeah? So now you see this ensemble average is by definition the cross correlation between the signal at x and signal at x prime. This is the correlation, yeah, by definition. So this copies down. So now we just need to change variables, okay? X minus x prime, x minus x prime. You just change a variable, make it x minus x prime, and some dummy variable, other things, and then this becomes that. So x minus x prime becomes x, x minus x prime becomes x, and this is what it is, yeah? And so you can see, you recognize this is the same as that. Just the xi minus xj become x, yeah? And so therefore this whole thing, it really is the eigenvalue of this matrix, as we know. So therefore the average signal power for the case Fourier wave, yeah, is actually the case eigenvalue of this matrix. So we see that the original signal, if you decorrelate into Fourier components, then the average power of this Fourier wave really is the eigenvalue of this correlation matrix. Okay, and now for different waves, you can have different Fourier, different eigenvalues. So this is a power spectrum. For this will become a power spectrum.